Welcome everybody. This is Math 105, Lesson 16, Applications of Dimensional Analysis, Part 2. Please start with a warm-up. We've got a European car. Fuel efficiency is given in kilometers per liter. We're going to convert that to miles per gallon. Now we've got a rate, so that means got to include both of those units, one on top and one on the bottom. All right, so we're going to have two conversions here. We're going to go from kilometers to miles using 1.61 kilometers is equal to 1 mile. And I'm positioning kilometers on the bottom so that it cancels with kilometers on the top. Now we're going to do liters to gallons. And there are 3.78 liters in 1 gallon. Now I've got liters on top, liters on the bottom, so those can cancel. And now multiplying straight across, I got 23 times 3.78. And then we'll divide by 1.61. And that gives us 54. And the remaining units are miles per gallon. So you can write that as miles over gallons or just MPG. Now we're going to be working with units raised to a power. And this is commonly used in things like area and volume calculations and other calculations as well. So one example of an area is square feet. You have square feet, square miles, square kilometers. And with square units, when we're talking about area, all right, we've got a unit of length on one side and a unit of length on the other side. You multiply the two lengths together and you get square units. So the same thing happens with units as happens with variables or with numbers. 2 times 2 is 2 squared. X times x is x squared. Feet times feet is feet squared. You can either write that as feet with an exponent 2, or you can just write out square feet. The same idea happens with volume. But with volume, we've got 3 dimensions: length, width, and height. So we're going to multiply 3 units together. Centimeters times centimeters times centimeters. That's centimeters to the 3rd power, or cubic centimeters. Now an interesting thing happens when we convert these units. And in order to demonstrate that, I'm going to write out miles squared as just miles times miles. It's called expanded form. So 1967 miles times miles over 1. So set up the same way we do the other ones. And now we're going to convert miles to kilometers. So 1 mile is 1.61 kilometers. Now notice what happens when we cancel. We can only cancel one pair at a time. I can't cancel both of these miles because I only have 1 on the bottom. So we cancel 1. And we still have miles on the top. That means if we have square units, we have to convert twice to get rid of both of the miles. All right, now I've got my other one there, so now I can cancel the other mile. And now look at what units we have left. We have kilometers times kilometers, which is kilometers squared, which is exactly what we're looking for. So we're going to take 1967, multiply by 1.61, and then multiply by 1.61 again. And that gets us 3166.87. Square kilometers. Now there is a shorthand way we can do this. We don't have to do 2 conversions like this. What we can do is just square everything in the conversion factor. So I'm going to write this one as miles squared. And when we do the conversion, we do 1 squared, miles squared, 1.61 squared, kilometer squared. Square everything, numbers, units, everything. Now we've got miles squared on top, miles squared on the bottom, those cancel. And now we're going to multiply 1967 by 1.61 squared, and we'll get the same value. Your turn number 1. You can use either syntax, doesn't matter. 18 square inches to square centimeters. The conversion factor between inches and centimeters is 2.54. So I got 2.54 centimeters on top, square both of those, 1 inch on the bottom, square both of those. Now I've got square inches on top, square inches on bottom, those cancel. We're going to take 18 and multiply by 2.54 squared. And that gives us 116.13 square centimeters. All right, your turn number 2. An HVAC technician is selecting a new heating system for a 2,400 square foot home with an average ceiling height of 10 feet. So we're given the area, and we're also given the height. Determine which model is appropriate for the home. The technician must calculate the air volume for the home, but the specifications of the manual are in cubic meters. So we're going to have to first calculate the air volume in the home. So we've got length times width already multiplied to give us area. Now we need to multiply that by the height. And then we're going to convert the result to cubic meters. So to calculate the volume, we're going to take area times height. So it's 2,400 times 10, which is 24,000. And feet squared times feet is feet to the third power. So 24,000 cubic feet is the volume of the home. Now we need to convert this to cubic meters. And the conversion between feet and meters is, one of them at least, is 3.28 feet per meter. So we're going to take this value, 24,000 cubic feet, multiplied by there's our conversion. 1 meter is 3.28 feet, and we're going to cube everything. So then we're going to take 24,000 and divide it by 3.28 to the third power. Those feet cancel, leaving us with meters to the third power. And that gives us 680.13 cubic meters. Now our next concept is going to be density, something used often in chemistry and in other fields. So density is a measure of how much mass there is of something in a certain volume. So cubic meter of iron is heavier than a cubic meter of water, so it has a higher density. And we're going to use density to spot fake jewelry. So the great mathematician Archimedes developed an ingenious method to determine the volume of irregularly shaped objects. The object is submerged in water, and then Archimedes would look and see how much much the volume of the water has raised. And the volume of the water that changes is exactly the same volume as the object. So Maria purchased a supposedly platinum ring, but it felt a little light and she wanted to confirm that it is really platinum. She brought the ring home and weighed it on a digital scale and read it out to be 0.206 ounces. Then Maria filled a graduated cylinder to the 10 milliliter mark and submerged the ring. The water level rose to 10.556 milliliters. Use the density formula and the table below to determine the metal that the ring is made of. All right, we're going to be able to figure out if this thing is a fake or not. And to do that, we've got this density formula. Density equals mass over volume. It's the amount of mass in a given volume. Now the volume is found by subtracting 10 from 10.556. All right, we put the ring in the graduated cylinder. The water level rose to 10.556 from straight up 10. And now we know the volume of the ring is 0.556 milliliters. And we also know the mass of the ring. That's given. She measured it to be 0.206 ounces. So now we can find the density, but if we find the density, it's going to be in ounces per milliliter. Now, the density of the metals are in grams per centimeter cubed. And as we saw before, 1 milliliter equals a cubic centimeter. They are the same thing. So I'm just going to go ahead and replace that. All right, same number. All right, but we are going to have to convert ounces into grams because the table is in grams. So before I go ahead and multiply this out, I'm going to throw a conversion factor on there. We got 28 point, oops, wrong side. 1 ounce is equal to 28.35 grams. And multiplying straight across, 0.206 times 28.35, and then dividing by 0.556, that will give us our density then in grams per cubic centimeter. And we multiply all that out, we get 10.5 grams per cubic centimeter. And if we look in the table, the metal closest to this is silver. So in fact, it is a silver ring, not platinum. Now, like I said, density is often used in chemistry. And what tends to happen a lot in chemistry is we get these chemical reactions. We need to know exactly how many grams of a substance are involved in the chemical reaction so we can figure out how much a reaction is going to occur and how much of the reagents we'll have left over after the reaction, things like that. However, liquids are often measured in milliliters. So if we measure out a substance in milliliters, we're going to need to do a conversion to figure out how many grams of the substance are in that liquid. And to do that, we use the density. So often, densities will be given in the problem, and the density itself is a conversion factor. Example 2. We've got 68.4 grams of a liquid with a density of 1.32 grams per cubic centimeter. All right, so we know how many grams we need, and we know the density of the liquid. So how many milliliters, otherwise known as cubic centimeters, are required? So we're going to start off with the given quantity, the mass we need, 68.4 grams. And then we use the density as a conversion factor to convert grams into milliliters. So grams are going to have to go on the bottom so that they cancel out. So it's 1.32 grams per 1 cubic centimeter. And grams cancel. And we'll take 68.4 divided by 1.32. That gives us 51.8. cubic centimeters, or 51.8 milliliters. Now we know exactly how much of the liquid we need. Your turn, number 4. An experiment requires 7.22 grams of acetone, which has a density of 0.7857 grams per cubic centimeter. Find the volume of the acetone in milliliters. Start with a given quantity, 7.22 grams. That's what we need. And we have a density here of 0.7857 grams per 1 cubic centimeter. Now we'll take 0.722, divide by 0.7857. And get 9.19 cubic centimeters, which is 9.19 milliliters. Now, in nursing, dimensional analysis has become the preferred method for doing dosage calculations. And the reason is dimensional analysis had been proven in scientific studies to be the method that produces the least amount of errors. Compared to the other methods used, fewer errors are made with this method, and that means that there's going to be fewer patients getting the wrong dosage of medication. So the number of people who die each year from medical errors, somewhere between the estimates say 44,000 and 251,000. So dimensional analysis ends up saving lives by preventing some of these medical errors. And the first example we're going to talk about is IV drip rates. So with IV drips, the fluids are in a bag and they're delivered into a drip chamber which drips at a certain rate. And then once it gets into the drip chamber, gravity takes the medication down and into the patient. And the drip rate controls how quickly the patient receives the medication. So basically the drip rate controls the dosage. Now there's some vocabulary we need to talk about as regards to dosage calculations. And the first is flow rate. So flow rate, the number of drops that enter the drip chamber per unit of time, usually measured in minutes. And the units here, are GTT, which is short for GTT, which stands for gutta, which is Latin for a drop. So GTT are drops, and we're going to be measuring things in drops per minute, or GTT per minute. Another vocabulary term, drop factor. This is basically a conversion factor for drops. And this is the number of drops in 1 milliliter of liquid. Different medications have a different viscosity, which means they have different size drops. So every medication is going to have a different drop factor. All right, so those are the two new vocabulary terms we need. Now we're going to answer this question. A nurse needs to administer a heparin drip to a thrombosis patient at 75 milliliters per hour. All right, so there's the rate that this person needs the medication. So 75, and it's a rate, so we put milliliters on top, and it's per hour, so 1 hour on the bottom. Now we're given a drop factor. The drop factor is 10 GTT per milliliter. So it takes 10 drops to make a milliliter. All right, so there's one conversion factor we're going to be able to use in this problem. And in a lot of these nursing dosage calculations, the conversion factors are given right in the problem. Now the goal is to have units of GTT per minute. Right? We want to figure out the flow rate in GTT per minute. So we're going to need to convert two things. We're going to need to convert milliliters to drops, and then hours to minutes. Now, fortunately, we're given this conversion factor here. 1 drop is 1 milliliter, or 10 drops is 1 milliliter. So we're going to be able to get rid of this milliliters right away. 1 milliliter and 10 drops. 10 GTT. Now we need to go from hours to minutes. So 1 hour, 60 minutes, and that's it. All right, so those are the two conversions we need. So we're going to take 75, multiply by 10, and then divide by 60. All right, so hours cancel, milliliters cancel. We're left with the units GTT, remember division bars per minute, GTT per minute. So we get 12.5 drops per minute. So in this case, the nurse would want to set the machine to be 12.5 drops per minute. Your turn, number 5. A nurse needs to administer 1,000 milliliters of D5W, which stands for dextrose 5 water, which means a 5% sugar solution in water. And this needs to be administered to a patient in 6 hours. The drop factor is 15 GTT, or drops, per milliliter. Calculate the flow rate in GTT per minute. So one rule of thumb with these dosage calculations is just start with that, whatever the doctor ordered. Doctor says 1,000 milliliters in 6 hours. Now we want the flow rate in GTT per minute. So we're going to have to change hours to minutes. All right, 1 hour, 60 minutes. Hours cancel. Now we're at milliliters per minute. So here we're going to use the drop factor, 15 GTT per milliliter. Milliliters go on bottom. Now we've got milliliters on top and bottom. Those will cancel. The units left are GTT per minute. And that's what we're looking for. So now we'll do 1,000 times 15 divided by 6 divided by 60. Which gives us 41.67 GTT per minute. And since it's really hard to count out a fraction of a drop, you usually just round this thing, so we'll do 42 GTT per minute. Round to the nearest whole drop. Now sometimes in dosage calculations we have to take the patient's body weight into account because the dosage of the medication depends on the body weight. So Medrol, a steroid used to control inflammation, is ordered for a child that weighs 64.8 pounds. The dosage is 5 milligrams per kilogram of body weight. And this happens a lot where dosages are measured in the metric system. The medication available comes in a strength of 500 milligrams per 4 milliliters. How many milliliters of Medrol should be administered? All right, so we're going to start with the dosage, 5 milligrams per kilogram. And we're going to convert this until we get to milliliters of Medrol. Actually, what we're going to do is start this one a little differently. We'll start this one with the child's weight. Because basically what we're doing is we're converting the child's weight into a dosage. All right, so the child is 64.8 pounds. Now, the dosage is given in kilograms. So the first thing we need to do is convert pounds to kilograms. And we can use the conversion factor 2.2 pounds in 1 kilogram. And then the other conversion factor is given in the problem. For every kilogram, we're going to do 5 milligrams. So milligrams from kilograms. All right, we've gotten rid of pounds. Pounds are gone. Now we're converting the weight of the child in kilograms to the milligrams of medication. Now we know how many milligrams we need, but we need to know how many milliliters to administer. So we need to do one more conversion from milligrams to milliliters, and it's given the problem that the medication comes in a strength of 500 milligrams per 4 milliliters. So we'll put 500 milligrams on the bottom, 4 milliliters on top. So the milligrams cancel, one on top, one on the bottom. And now we've gotten rid of all the units except for milliliters. And that's what we want. So to figure this out, we're going to take 64.8, multiply by 5, multiply by 4, then divide by 2.2, then divide by 500. So that gives us 1.18 milliliters of this medication. Your turn, number 6. A 215-pound patient with an infection is ordered 7 milligrams per kilograms of vancomycin. The medication available comes in a strength of 375 milligrams per 10 milliliters. How many milliliters of vancomycin should be given? So we're starting with the weight of the patient, 215 pounds, and we're going to eventually convert this into milliliters. So first thing, just like before, we're going to convert to kilograms. Then use the conversion factor in the problem that tells us how many milligrams per kilogram of body weight, and that is 7 milligrams per kilogram. So 1 kilogram goes on the bottom, and 7 milligrams of vancomycin on top. So let's see what we got here. Pounds cancel, kilograms cancel. Now we're milligrams. Now we can use the medication strength, which is 375 grams in 10 milliliters. Or 375 milligrams. 375 milligrams per 10 milliliters. And now we've got milligrams canceling. And now all we have to do is multiply square root cost, 215 times 7 times 10, and then divide by 2.2, divide by 375, and we get 18.24 milliliters of vancomycin. All right, now we got some really tough ones. Calculating the power cost. So a homeowner in a humid area is considering purchasing a dehumidifier but is concerned about the power cost. The dehumidifier consumes 400 watts of energy. The homeowner checks the electric bill and sees that the electric company charges 15.8 cents per kilowatt hour. If the dehumidifier will run for 8 hours per day, how much will it cost to run for 30 days? Now there are a lot of different ways to set this one up, and they're all valid as long as the units we don't want cancel and the units we do want end up in the answer. Now, kilowatt hour is running 1 kilowatt for 1 hour. So it's 15.8 cents per kilowatt hour. All right, now we want to know what the bill is in dollars. Cents aren't going to help us that much. So 100 cents per dollar. Okay, now we're in dollars. Cents cancel. But our usage is given in watts. So kilowatts on the bottom top cancel. And we know running at 400 watts. Now traditionally this would have been the first fraction given, but like I said, order doesn't matter. Now the only thing we have left to do, since we're talking about a time period of a month, is we need to convert this hour into a month. All right, so hours to days, hours cancel. And then 30 days in a month. And let's see what units we have left. Everything's canceled except for dollars on top and months on the bottom. So I did this in kind of a weird order just to show you that it can be done in any order. As long as you line up your units right, you get good cancellations, and we're left with the units that we want. So now to get the answer, we're going to multiply all this stuff on top, 15.8 times 400 times 24 times 30, and then we'll divide by 100 and divide by 1,000, and that's it. That gives us $15.17 per month. Not bad. Your turn, number 7. A space heater consumes 1,500 watts of electricity. If electricity costs 13.7 cents per kilowatt hour, how much will it cost to use the space heater for 6 hours per day over, I made a mistake. We aren't running it for 24 hours a day. I put the wrong number in here. That should be an 8. Okay. Back to your turn, number 7. How much will it cost to use the space heater for 6 hours per day over 120 days? Now, traditionally, one starts with the single quantity. The quantity with only one unit is 120 days. So we could start there, work off of that one. And then we're going to only use the space heater for 6 hours per day. All right, so that'll give us the number of hours we're going to run the space heater. 120 days, 6 hours each, multiply it out, we get the number of hours we're going to run it. And now to get rid of hours, we can use the cost. 13.7 cents per kilowatt hour. And now hours cancel. The space heater consumes 1,500 watts of electricity, so we'll need to get out of kilowatts and into watts. So the 1 kilowatt, 1,000 watts. And we are in cents, so we're going to need to convert to dollars, 100 cents. There's $1. So cents are gone. We got kilowatts gone. And what do we need left? We need to get rid of watts. We want dollars. And so, last thing, we're going to multiply by 1,500 watts. And now watts cancel. And the only units we have left are dollars. So we're going to take 13.7 multiplied by 120, multiplied by 6, multiplied by 1,500, and then divide by 100, divide by 1,000. we do all that, we get $147.96 to run the space heater for 120 days. So that's about as challenging as those problems get. So if you can handle these, you can handle anything. That's it for today. Have a great day.